So now that we're all on the same page about what Spark is, I'd like to dig a little bit deeper and talk about exactly why it's so popular and some of the things you'll be able to do with Spark. So when it comes to big data, Hadoop has pretty much been running the show for the last 10 years. And while drastically simplifying distributed computing, combined with the increasing availability of the cloud to provide inexpensive computing resources, Hadoop really did make big data analytics possible for the masses. And if you haven't read the research papers published by Google in 2004, which led to the development of the open source Hadoop project, you really should. They provide a great background in overcoming the challenges of distributed computing by describing the MapReduce framework and its distributed file system. But even though Hadoop has been an incredibly successful product, allowing people to do things that were previously impossible without hugely expensive data warehouses, there are two main fundamental issues which become limiting when trying to expand Hadoop beyond its original purpose of indexing websites. First, it has a very rigid programming model, and while many data analytics problems fit very nicely into the MapReduce paradigm, many also do not. As a result, a lot of real-world problems require complex engineering to be written as a Hadoop program. For example, calculating a mean average of a list of numbers requires some surprisingly complex programming to make it happen. Here's an example mapper and reducer class to do that, which even if you aren't familiar with Hadoop, you should be able to recognize that there's a lot of tedious and potentially error-prone code in this example, like forcing all the data into key-value pairs and manually looping through the list of numbers keeping track of the counts and sums to write the average to the output writer. To help this, tools like Hive and Pig popped up to try and add these extra capabilities by exposing a higher-level API. But since all they do is translate a more abstract program into a Hadoop MapReduce job under the covers, they do little more than band-aid the problem. And as a result, a Hadoop developer is required to also learn Hive, and also learn Pig, and also learn cascading, etc., in order to be able to solve real problems. Now it also is slow. Slow is a relative term when we're talking about big data scale, and a job can vary greatly in performance from the configuration and tuning on the cluster, but when we talk about Hadoop being slow, we're mostly referring to the fact that it's a disk-bound batch processing engine. Every job begins with reading data from the distributed file system and then ends with writing it back. Again, when looking at real-world usage, you'll often want to read a dataset once and then perform multiple stages of transformations before storing any results. With Hadoop, doing this requires multiple iterations of read, process, and write. Now consider our word count example from the last video. Let's say we also wanted to know some statistical information about the data. For example, the mean average occurrence of words, or what word appears more often, things like that. Doing this in Hadoop requires separate applications, each of which reads in the base data input set and performs the specific processing for that statistic. Now that doesn't sound very efficient, does it? Enter Spark. Created by a research team at Berkeley to build a faster, easier to use big data processing framework. Now in contrast to the disk-bound approach Hadoop uses, Spark is based on an in-memory execution model, so applications that can run iteratively like we discussed earlier will perform exponentially faster on Spark. In our previous example, where we wanted to both count and get some stats on the data, with Spark you would read the data once, cache it in memory, and then do whatever additional processing you wanted on that in-memory data, all within one same application. And while Spark can certainly operate on batch data and HDFS just like Hadoop, it also supports a much larger set of storage options, from other disk file systems to cloud storage and databases. Pretty much any source of data can be processed by Spark. Possibly most important is that Spark is built with a flexible API that allows for more diverse workloads than forcing the input to be broken down into key-value pairs and doing MapReduce. You can also write your Spark applications in Java, Scala, Python, and R. Finally, it provides a rich set of processing operations you can do on your data with simple function calls. Spark has a much more cohesive programming environment where all of this functionality is included directly within the Spark environment, as opposed to Hadoop where you have to add on separate products. So now let's take a look at the modules available in Spark. First is the Spark Core. This contains the basic functionality for running applications, distribute them across a cluster, coordinating execution, etc. It also provides the foundational data abstraction known as an RDD that removes all the complexity of working with distributed data. So we'll soon talk about RDDs in great detail. Spark SQL. On the surface, Spark SQL allows you to manipulate distributed data in Spark using the SQL language. However, this functionality is combined with two other concepts called data frames and datasets, which simplify programming even more and have significant performance enhancements as well. This is probably the most widely used set of APIs in the framework, and we're going to take a deep dive into this in Unit 3. Spark Streaming. This allows for analyzing streams of data using the same programming constructs as the rest of Spark. It provides an additional abstraction over RDDs to let you work with streams of data the same way as batch data, so you can use the same libraries and functions for both your real-time and streaming applications. And Unit 4 will be devoted to Spark streaming. Spark MLlib. This provides implementations of many common machine learning algorithms and patterns in Spark, and again, this is applicable to both batch and streaming data. However, machine learning is an incredibly complex subject, and we won't be covering it in this course. Finally, Spark GraphX. This introduces a way of processing graph data in a distributed manner, and like MLlib, provides implementations of common graph algorithms like PageRank and shortest path. Also, like machine learning, graph analytics is a complex enough topic to have its own course, so we won't be addressing it in this series of videos. Phew, well that was a lot of background information, but it's important to understand why Spark has become so popular and taken over the analytics world. Next, we're going to actually get to do some work and take a look at the programming environment for Spark over the next two modules. So let's have some fun.